Alright, this is a tricky one. I'm not going to lie to you. So what we have here is we've got some temperature and we've got a diameter. Now, careful on diameter. We can treat that just pretty much the same as a length. I know it sounds weird, but we can. You need to slip this over a steel shaft that has a room temperature diameter of that. So we need to get this aluminum one to increase a little bit. So what common temperature should this should the ring and the shaft be heated so that the ring will just fit onto the shaft? All right, I'm going to start calling diameters capital D here. Not sure why, but I am. And the diameter of the aluminum in its final state has to equal the diameter of the steel in its final state. Then what we can say is the diameter of the aluminum initially, I know this is weird, plus the change in diameter of the aluminum has to equal the diameter of the steel initially plus the change in diameter of the steel. For some reason I was putting these in parentheses, so I'll continue doing that. We're going to go back to this, the change in diameter of the aluminum initially. I am going to call this, I'm going to treat that just like a length. And we have to go back to our little equation of change in L equals fishy, which is coefficient, times the original length times change in T. Everywhere I see this, I'm going to replace it with that because it's change in L. So I'm going to replace this with what the change in this diameter would be, which is really just kind of a length. So I'm going to replace that with the fishy, the diameter of the aluminum, because that is the original length, if I'm over here looking at that, and then times a change in T. That's where my change in T is going to come from. And I'm going to do the same thing over here with the diameter of the steel. Why is there a... This should have been a T here, steel, and then the initial should be out there. So steel's inside. So the diameter of the steel initially plus, and I'm going to do the same thing over here. This is going to be a change. It's just like a length. I'm going to have the coefficient of, oh, I should have put aluminums over here, AL, change in temp. This is the fishy of steel, the original length of the steel, which is just the diameter of the steel, just like I did over there with aluminum, and the change in temp. All right, you're going to love this. I am going to subtract this D diameter of aluminum initial, and I'm going to bring this, I'm going to subtract this diameter of steel initial from both sides. I love this. This is, remember doing these little games in algebra class, wondering when would you ever use this again? This is when. So if I subtract that from both sides, I'm going to have to take this and subtract it from both sides. So on this other side, I believe I put steel first. Yep. So I'm going to put this first. So I'm going to have the coefficient of steel, diameter of steel. I'm right there with the green. Change in temp. But then I got to bring this blue back over and I have to subtract that from both sides. So that's the fishy of aluminum, coefficient, diameter of aluminum, and change in temp. I love this. All right, let's factor out a change in T over here, because why wouldn't we, right? So I still have the DALI over here. Whoops. Minus diameter steel. I don't know why I'm putting these parentheses in there. Just leave me alone, would you? So if I factor out a change in t, I'm going to have a coefficient of steel multiplied by the diameter of the steel minus coefficient of aluminum times the diameter of aluminum. And now I gotta get this change in t all by itself. And I'm going to run out of colors. I'm going to take this and divide that by both sides. And I'm going to bring that over here. It's the coefficient of aluminum, diameter of aluminum. That's gone. I'm left with just that equaling this. And these all I can put numbers in for. Isn't that crazy? My diameter of aluminum initially, whoa, what was that, dude? Was 2.500 centimeters minus 2.506 centimeters. Coefficient of these things over here is 12 e to the negative 6. Yes, I used the e. Would you just lay off? It's like last year all over again. 2.506 centimeters is going to be my diameter. I might have just kind of realized here, I lost some initials up here along the way. The diameter of the aluminum initially. Anyway, you just got to trust me on this one. 2.506 centimeters. And then I'm on the second half of this red part over here. Coefficient of aluminum is 23 e to the negative 6 Kelvin, negative 1. And the initial of that was 2.500 centimeters. And what you're going to get is a change in t after you throw all that in your calculator. Careful, there's a lot of order of operations there. But I'm getting a change of t equaling 218 Kelvin. But if it changes by 218, we started at 20 degrees Celsius. So the change in T is 218 Kelvin, which is equal to 218 Celsius. But I started at 20 degrees Celsius, so it's going to have to change up to 238 degrees Celsius. You might want to do this math really carefully there. Anyway, 8.5, almost 9-minute video. Oh my God. Bye-bye.